All right, so we're going to continue talking about equilibrium. Remember that our conditions for equilibrium, our consequences of equilibrium, are that F net in all three directions are equal to 0, and that tau net about any axis is equal to 0, and therefore it is very important that you tell me what that axis is going to be. Okay? Definitely label it on your picture. If you're going to apply tau net equals 0 more than once, then please tell me this is tau net around the origin, this is tau net around the other end of something. Okay? So let's do page 347, number 30. If somebody could read it for us, please. Okay. So again, I have this object that's just hanging out. It's not going anywhere. So it is in what? Equilibrium. And I'm trying to find a bunch of forces. So if I'm trying to find a bunch of forces, what am I going to do first? Free body diagram. I got to make my free body diagram first. And the question you have to ask yourself is, what am I going to make a free body diagram for? Well, will that have all of my forces in it? No, because I need to know the forces on the hinge. I need to know the tension in the cable. Is there a single object that all of those things act on? The rod. Okay? And even though the rod is massless, I can still make a free body diagram for that. Because I already know that F net equals MA is going to be equal to 0. So it doesn't matter that the rod doesn't have any mass. And I already know that tau net is going to be equal to 0. So it doesn't matter that the rod doesn't have a rotational inertia. Okay? So I thought you all were supposed to go downstairs at 9:50, right? If you were going to participate. Okay? So we will pause class. All right. So we're going to draw a free body diagram for the rod. Okay? So here's the rod. And what are the forces that are going to act on it? Okay, so there's going to be tension from the cable at this end at some angle theta. What else? Well, the sign is attached. So there's going to be a force from the sign. You're right. And so actually, because it's a uniform sign and it's attached at two places, the gravitational force for the sign is going to be equally divided between those two contact points. Yeah, so this will be Fg over 2, and this will be Fg over 2. And what else? Right, so the rod doesn't have its own gravitational force. Yeah, the hinge. Well, it's like a normal force. Okay, it's going to effectively be pushing back on the rod. And we're lucky because in this problem, it talks about finding the horizontal component and the vertical component separately. And again, this is a third law pair kind of thing, that the rod would press against the wall via the hinge, and so the wall via the hinge is going to push back on the rod. So what's missing from my picture? Axes. So I'm just going to give us standard axes here. And then what are we going to do? Yeah, probably F net equals MA. It's always a good place to start. So you want to start with X or Y. Okay. So we know that F net Y is going to be equal to 0. You have your picture there in front of you. So what are my forces in the Y direction? Okay, so there's a Y component of the tension. What else? Okay, so there's the vertical normal force. So, yeah, I can really just write it as Fg because if I'm only concerned about the vertical direction, it doesn't really matter that it's applied at two different places. Okay. So Ty, positive or negative? Positive. Vertical component of the normal force, positive or negative? I've drawn it positive, but I don't know what it's going to be. So if I leave it positive, it'll pop out with a negative sign. We'll know we were wrong and life will go on. Gravitational force. So I know that Ty plus NV is going to be equal to mg, right? What should I do next? F naught x. What are my forces in the x direction? Okay, so I've got Tx, and what else? Okay, so the horizontal component of the normal force. Tension X, positive or negative. Horizontal component of the normal force, positive or negative. So I know that NH is going to be equal to Tx. So how many unknowns do I have here? Really? No, we do not have tension. I want a number. How many unknowns do I really have? 3. What are they? Tension, NV, and NH. Because I know that Tx and Ty, I probably can express those in terms of the tension. You don't, but look at your picture. Here's going to be my angle theta. But I have two sides of a right triangle, so effectively I have the angle. Okay? I know that this part's going to be 3 here, and then this is 4. So actually I even know what the hypotenuse is going to be. 5. So I don't really need to find the angle as much as know what cosine and sine of the angle are going to be, which I do. Okay? So I have 3 unknowns. How many equations do I have up there? 2. Okay, so what am I going to need? I need a third equation. I've already used x and y. There's nothing in the z direction. So where do I look for another equation? I look at torque net is going to be equal to 0. But I need to pick an axis of rotation. Where do you want it to be, Priya? Why do you want it to be there? Again, why do you want it to be there? Okay, so if we put the axis of rotation here at the hinge, then both the torques due to the vertical component of the normal force and the horizontal component of the normal force will be 0, right? These two things cannot have a torque on that point because what's their moment arm? 0. All right, and it's like pushing or pulling on the hinge. You know that doesn't work. It's not going to turn anything. So like Casey said, that means that the only unknown I'm going to have is the torque. Okay, so you with us? Okay, so we're going to do our axis of rotation located at the hinge. And like I said, you have to, at minimum, label it on the picture. And it would be awfully nice if you wrote it above the place where you're going to actually do the work. Okay. So we got to look at everything that could have a torque, right? So I could have a torque from the vertical component and the horizontal component of the hinges. What else could I have a torque from? Tension. I think it's better if you actually just go from one end to the other. Start at the axis of rotation and go down, because now what are we missing here? I got 2 more torques. So I've got Fg over 2 and another Fg over 2, right? Because now it matters where those gravitational forces are applied. Okay. And what's the formula that we use for torque right now? Okay, we can use R cross F, or probably more importantly, RF sine phi. Okay. So we can simplify this a little bit, right? What can I get rid of? Yep, we just said that the torques due to both of the normal forces are going to go away because their moment arm or their R value is equal to 0. And then how about the torque due to the tension? Is that going to be positive or negative? Okay. It's going to pull it this way. What do you think, Priya? Okay, so then the torques due to the gravitational forces are going to be negative. And really, you better make sure that you have a mix of negative and positive torques because you need them to cancel. And if they're all positive, that's a problem. Okay. So using our formula up here, what's the moment arm for my torque due to tension? Okay, so that's going to be 3 times the tension times the sine of what? I labeled it as theta. Okay, because this is my moment arm and this is my torque. And so the angle between them is theta. No, not yet. I'll eventually want you to find the angle, but right now we're just trying to fill things in. You with me, Casey? Okay. All right. How about the moment arm for that first gravitational force? 1 meter. And then it's mg over 2 times the sine of what? 90. I get concerned when we try to skip too many steps when you're doing a problem like this. So I think it's better to do one thing at a time. All right, what's the moment arm for my second gravitational force torque? 3. Again, mg over 2. Again, sine of 90 equals 0. And the sine of 90 is 1. So I've got 3 times the torque, or I'm sorry, times the tension. And then what's the sine of theta going to be? Okay, opposite over hypotenuse. Okay. So that's going to be times 4/5 minus 1 mg over 2. Sine of 90 is 1 minus 3.0 mg over 2. That's going to be equal to 0. So I think this should give me 2 mg over there, right? Because I've got 3 halves plus 1 half. Should give me 4 halves, which is 2. And, yep. So T is equal to 10/12 mg, I think. So what's that going to give me? M is 50. Yeah, you did. Okay. So how many sig figs do we have floating around? 3? 2? Well, my copy from the book has 50.0, 2.00, 3.00, 4.00. So I think we've got 3. Okay. And what's my unit, of course? Newtons. Okay. So that's good for the tension. Okay, so now I need to go back and solve for NH and NV. So let's write those again on another sheet. So I've got NH is equal to TX and TY plus NV is equal to MG. So NH is going to be the easiest, because how do I write TX? I'll go back to the picture. What's TX is going to be here, so that's going to be T cosine theta. So that's going to be T, and what's the cosine of theta? Should be, right? Adjacent over hypotenuse. So we know that T is 408 newtons times 3/5. So NH is going to be Yep, I agree with that. Now, this popped out with a positive value. You should ask yourself, does that make sense? Okay, why? Okay, so Casey's argument is if the rod is pushing against the wall via the hinge, then the hinge should push back in that direction. Another argument you could make is that the tension force is going in the negative direction, and if I'm not going to have a net force in the x direction, my hinge force has to point in the opposite direction. Okay, makes sense? Reality checks are good. Okay, so now we need to solve for NV, which is going to give us mg minus ty. And ty is going to be t times what? Okay. And what's the sine of theta? 4/5. Think about it before you ask me. So that cancels with that. That's a 3, that's a 2. So that makes my NV mg over 3. I do believe. Which is going to give us what? So for 3 sig figs Maddie, that'll give us what? 164 newtons. Okay. These are pretty straightforward. There's some algebra. You need to be careful, but they're pretty straightforward. Okay. This is, you're more likely to get a question like this on the multiple choice part of the AP exam than on the free response part. Okay. Usually towards the end somewhere, there'll be some loop or something will be hanging off something, and you figure it out from there. Okay, and that's a multiple choice question. All right, we good? Okay, so let's do the ladder problem. Well, it's more that it's a class of problems. And it's not a problem that you have in your book, so I'm actually going to type it out because it'll just be easier to do it that way. Okay, so a uniform ladder of mass m and length L leans at an angle theta, because I don't know how to type that out, against a frictionless wall if the coefficient of static friction between the ladder and the ground is mu. What is the minimum angle at which the ladder will not slip? So of course we're going to rewrite that as mu and rewrite that as theta. Correct. This answer will be in terms of the things that are given, which is something that we need to practice for the AP exam, because the AP exam often has answers that don't require numerical answers. But you need to get used to giving an answer in terms of things that are given to you, and little g, and big G when we get to big G. The universal gravitational constant, 6.67 times 10 to the negative 11th newtons meter squared per kilogram squared. We got 2 more chapters to go after this one, which is why we're going to finish this chapter tomorrow. Yes, they are short chapters. And if you look, I believe on the portal, things have been updated, like when this homework is due and when this test is, which I think is next Friday, because we need to finish this, and we will. No, it's on Monday, because it's a test on chapters 10 and 11, and it had to be a double, and we were not ready to have it today. Yep. We had a quiz on chapter 10. We did not have a test. Okay, everybody write down what the problem is. Okay, so basically, I have my wall here. Actually, I'll make my ladder a different color. I have my ladder. My ladder has some length L. It's at some angle theta. That's where I made my theta, so that's where theta goes. Okay. And I want to find the minimum theta. So ultimately, I am going to solve for theta. Okay. What do you think I need to do? Right, when in doubt, free body diagram. Okay, so the ladder is the only object I have. So I'm going to make a free body diagram for the ladder. What's on my free body diagram for my ladder? Okay, so there's going to be a gravitational force for the ladder. Where is that going to be applied? At the center. It's actually, yes, but it's actually, like we talked a little bit yesterday, at the center of gravity, which for a uniform object is at the center of mass, if that uniform object is in a uniform gravitational field, which the ladder is. What else? From what? Okay, so there's a normal force from the wall and a normal force from, I think I called it the floor, even though maybe it's on the ground. And what else? Oh, it's okay. Static friction force. And which way is that static friction force going to point? Yeah, because which way would the ladder go? Yeah, so the ladder would slide this way, so I need my friction force to go the other way. Now they tell us that the wall is frictionless for whatever reason. We're leaning up against a window, I don't know what, okay? Solar panel, something. So there's no friction force up there. So now what's missing from my picture? axes. So again, we're just going to give standard axes because everything's going to go to 0 anyway. It's kind of arbitrary. And now what do I do? F net equals MA. All right. We're going to have to do X and Y, so I'm just going to start with X. So I've got my friction force and the normal force from my window. Friction force, positive or negative? Normal force from the window, positive or negative? So this is cool because that says that my friction force is equal to the normal force from the window. Sure. Excellent question, and we're going to answer that right now because I want to write my friction force. So normally, yes, friction force is what? Mu times the normal force. Where is this friction force acting? On the floor, right? So it's going to be the normal force from the floor. And what am I solving for again? Right. Okay, so I still don't even have theta in here, which is kind of crazy. But I got some other stuff I need to know. I'm also going to do F net Y is equal to 0. Give me something useful out of there. What's that going to tell me? Okay. Sure. Equals NW, which is beautiful. Except that I don't have an angle anywhere. Maddie, save us. Bingo. Okay. So where do you think we should do the torque around? Probably the floor, because I don't know what any of those things are. Okay. So that's going to be my axis of rotation. So I'm going to find the torque around, well, the contact point between ladder and floor. So I know that tau net is 0. So I could have a torque from the floor, I could have a torque from the friction, I can have a torque from Fg, and I can have a torque from the normal force on the wall, right? What do I know about these two? Why are they 0? Because their moment arm is 0. Torque due to the gravitational force, positive or negative? Negative. Torque due to the normal force from the wall? Better be. So basically, I've got tau Fg is equal to tau Nw. So what's my moment arm for the gravitational force? L over 2. So this is going to give me L over 2 times mg times the sine of what? Well, phi, but this is theta, and theta and phi are related, right? 90 minus theta. What's the moment arm for my wall? Normal force due to my wall. Okay. And W, sine of what? What's that? Theta, alternating interior angles, yes? Whoa, it all comes back, man. Live it. Okay. So, I've got L over 2, mg sine 90 minus theta L. And W is mu mg. Sine theta. I can cancel the L's. I can cancel the mg's. Wait for it. Sine of 90 minus theta is also known as the cosine of theta. Look it up. Live it. Prove it to yourself on a right triangle. So basically, I have tangent theta is 1 over 2 pi. I'm sorry, 1 over 2 mu